Hey guys, this is Test 49 Game 3. This is the Summer Program Courses game. It's an in-out game, also known as selection. We know this because they start by telling us that the program offers at least one of these courses, meaning that not all of them have to be offered. And then, of course, if you look at the rules, you see that they're all conditional statements, meaning that if something is in, then something else is out, or if one thing is in, then another thing is in, and so on. So we see the same variables featured in multiple rules. For example, we've got z in the second to last rule and the last one. We've got p in the second and third rule. And then there's some other linking there too. So this suggests that many of the rules will link together to form long conditional chains. So I'm going to lay out the rules one by one and link them together as I go. So they start by telling us that if we have M, then we have L or S, meaning if we have L, if M requires L, then it doesn't require S. Contrapositive, the alternative would be if we have M, then we might lack L, yet still have S. So this one's kind of annoying from the start because you don't really know which way M's going to go on this. So let's leave that alone since it's somewhat ambiguous and focus on the rules that are more concrete. So we've got L, then G, but not P. So if we have L, then we don't have P, and we do have G. Next, contrapositive. If we have P, then we lack L, and so L requires P, so P requires not L. L requires G, so then we'll say that not G requires not L. Next, they say to us, if we have S, then we have P but not Z. So if we have S, then we will have P, but S also requires not Z. Contrapositive, if we don't have P, then we don't have S. And then, of course, we also know that if we have Z, then we don't have S. So things are starting to link together somewhat here. Next, they tell us that if we have G, then we have both H and Z. Now, you'll see here that I wrote Z all the way up top. I can't really easily link it to G where it is right now, so I'm actually going to take that Z and put it down here instead, saying that Z requires not S once again, which is still valid like before, but now I'll say that G requires Z. Also, of course, G requires H. Contrapositive, if we don't have Z, then we don't have G, and if we don't have H, then we don't have G. So now if you look at this, you see that when we have L, we don't have S, and when we have S, we don't have L. So they didn't really need to say that M doesn't require both of them, of course, because you could never have both L and S simultaneously anyway, since one in requires the other out. Rather, they could have just simply said that M requires L or S, period. So we could say that, keep this on the side there, remember it, of course, but it's not really that much to worry about. It just means that M leads to one of these two chains starting, although we don't know which one. And of course, in a world where you have M, you've also got to have at least one of L or S in as well. So this right here is our initial setup for the game. Now, question number 13, typical orientation question, just take one rule at a time and apply that rule to all 5 choices, looking for violations. So of course, we could start by looking for the rule that when we have M, we have exactly one of L or S, it turns out, of course. So choice C has M, yet does not have either L or S, so that's gone off the bat. C is eliminated for 13. Then D has M, yet has exactly one of L or S, which is good. E has M, yet has both L and S. That's unacceptable. So for that reason, we can eliminate E. Now we could use some of the other rules that we got here. We know that, for example, when we have S, we have P but not Z, but none of the remaining choices has S, so that's not going to be useful. We could use the rule that when we have G, we will have both H and Z. Using that, we see that B is invalid because it has G, yet does not have Z. Now we're down to A and D. We could use the rule that when we have L, we have G but not P. And of course, we see that in choice D, we have L, yet we also have P. Unacceptable, so D is gone, leaving A by elimination for number 13. Next, number 14, if we have L, what could be true? So of course, when we have L, all of this follows automatically, the entire chain. So I'm going to make a little in-out table here. When we have L, we lose both P and S off the bat, because L in requires P out and P out requires S out. We know that L requires G, so G will have to be in, and G requires both Z and H. So those have to be in as well. Now, what could be true? Could S be in? No, S is automatically out, so A is gone. Could H be out? No, H has to be in, so that's automatically impossible as well, and B is gone. Could we lack M? Yeah, we don't know where M is. M is on the fence here. Could be in, could be out. I'll even draw it right there. M's on the fence. So we don't know which way it goes. Sure, it could be out. That's fine. So C works. It's our answer. I'll look at D and E, though. A total of 2 courses are offered. No. We got to have at least 4 here. That's impossible. Then looking at E, Z is not offered. Well, Z has to be in, so it's impossible that Z would be out, and E's gone, leaving C if you didn't get it before. Next, number 15. If H was out, what else could not be in? Well, if H is out, we know G is out and L is out. So I would look for G or L being listed as something that could not possibly be in. G is not a choice, but L is, so A is our answer for 15. Next, number 16. If we have M, then what must be true? So of course, M just requires exactly one of L or S in. We don't know which one. So A and C can automatically be eliminated because we don't know whether M is going to be with L or with S, just that it has to be with exactly one of the two. P, we don't know because M does not impact P. M is not involved on these chains. It's only involved in the OR rule at the beginning. So for that reason, B is gone as well. Then looking at D and E, at least 3 versus at most 4. Well, when we have M, one of these 2 chains will be activated, and we know that the L chain has L, G, Z, H, and the S chain has P. So we can't necessarily say that at most 4 are offered, because if we have M on this chain, we're going to have M, L, G, Z, H, which is 5 things. So 4 is not the max, and E's gone, leaving D by elimination. And if you look at D, at least 3 courses, well, yeah, because if we have M on either chain, on the top chain we have 5 things as a result. On the bottom chain we have 3, M, S, and P. So either way, you have 5 or you have 3, so at least 3, definitely D is our answer. Next, number 17, what must be false? So 4 of these things could be true. You could find the 4 that could be true and eliminate them, and whatever remains will be your answer. Or, of course, if you see something that works, just pick it. So could we have both G and P? Yeah, they don't conflict. It's not like one of them being in leads to the other being out. G in simply leads to Z and H in and S out, and P in simply leads to L out. So they don't conflict. They could be together. A is gone. G and M. M's not even on these conditional chains, so we could certainly have both of them if M, for example, were activating L rather than activating S, so B is gone. Next, looking at C, both P and M. Again, M's not involved in these 2 chains. If M were on the bottom chain causing S, then of course we could have P with it, so C's gone. Looking at D, H and M. If M were on the top chain, then it would definitely lead to H in. If M were on the bottom chain, we don't know whether H would be in, so D's gone. Then E by elimination. Looking at it, both G and S is impossible because G in leads to S out, S in leads to G out, so whenever one of them is in, the other is out. So E is our answer for 17.